Well, thank you very much. Doug is not able to join us today, so I get the honor to represent a project that we're both partners on. And I have to start off by saying howdy. I just arrived back from Texas, A&M University, where I was doing a similar talk, and everything you have to start off with is howdy, so work with me. Howdy! Thank you. I want to talk about biomass, I want to talk about inventory, and I'm happy I'm behind a podium because usually when you talk about inventory or the forest resource inventory, you either have people that want to throw things at you or applaud you. So I'm going to sort of set to the side of it here so I can look at the slides, because somewhere between the back of the room and here I have left a diary. It's a black 8x10 hardcover with a blue sticker with a sailboat on the top. I'd love to get that back today because it contains all my speaking notes and quite a few other notes as well. Talk about biomass. A lot of people talked about inventory and our uncomfortable nature around some of the estimates of inventory. I want to tackle that very quickly. You're going to get the much music version of this talk because we're pushed for time. So I want to talk about inventory. How many people here use forest resource inventory maps as part of their job? So there's quite a few people. How many people feel great about the quality of the information? If I said go to Highway 11 and 64, what's the volume of that stand right on the corner? Would you feel good? So we have some problems with knowing exactly where is this volume or this biomass. We also have issues with, well, does the inventory have the correct age assigned to it? So if it's 100 years old, I know sort of the range of sizes I'm talking about. How comfortable are we with that? How much is really out there? We hope that the law of averages, because the forest resource inventory in its inception back in the 50s was a strategic inventory, we hope that it would all average out across our forest land base. But now as we get into spatial modeling and we're looking at spatial habitat requirements and leaving things set aside on the landscape, it's important we know that that polygon is what it says it is. And I think as we talk about developing business plans towards biomass harvesting and sustainable forest management, we want to have better information at that local scale. Species. We all know this species is off, it's plus or minus, and we're basically using human eyes to interpret the species classification. So I want to talk about how we're trying to move forward from that. Are you sure? I think we could probably say we're not so sure. Joe talked about it, Peter talked about it. There's sort of comfort level with the inventory. We think overall it's good, but I think it's time that we start to focus in and look at that smaller scale and get more comfortable with the estimates as we make our modeling and our management decisions. Does it matter? Yes, of course it matters. I'm going to skip over this. There's all kinds of studies that have documented the issues with inventory. And I'm not trying to take shots at the inventory, but there are things where species classification is off by 50% when we start looking at stands. That's pretty severe. Remember Joe's example of where we're looking at different volume that's recovered as a percentage from the roundwood to the tops and the branches. Well, if it was maple was estimated and an X amount of volume gain from the branches and the top of the tree versus oak, there's a huge difference in that amount. So we want to get those percents correct. Other stuff work in the boreal forest found similar things where 64% of the stands were misclassified. And as well, the law of average for some of the forest units in terms of volume or yield didn't average out. So there are some issues. And the new Ontario's commitment to forest resource inventory is looking at trying to improve these estimates. What I'm going to talk about today is not what the current inventory plans are. This is sort of the R&D side, where we think the next evolution of inventory will take us, and hopefully we'll implement this more in the short and medium term than the long term. I want to talk about these advanced forest resource inventory technologies. I'm going to talk about two things. And again, sort of like Suzanne and Trevor, we're basically talking about a whole host of partners. And some of the main partners, the Canadian Wood Fibre Centre, along with M&R and Tembec, the Forest Research Partnership, and some consultants at Queen's University, are all looking at these different technologies to improve our inventory. I want to talk about two main inventory techniques, or remote sensing techniques. One is LiDAR, which I'll explain in a second, and the other is using semi-automated image analysis. So instead of just solely relying on an interpreter to look at a photo and come up with a species classification in our stand polygons, how can computer technology help us in that? And the final piece is basically fusing those two things together, because as you'll see, each gives us certain strengths, but together they're much more powerful. Quickly, LiDAR is basically flying, for our work was a airborne sensor in a fixed-wing aircraft. It's a scanning system, and it sends out pulses of near-infrared light. And as the pulses of light hit an object, top of a tree, a car, a moose, a signal is returned back to the sensor, and because we know the speed of light and we know where the aircraft is with GPS technology and all kinds of other high-tech stuff, we can actually place that dot in time and space. That's all this, the quick version. This is an example of what LiDAR looks like. This is basically looking straight down on the LiDAR cloud. It's colored by elevation, so the yellowy green is the low and up to the blues and purples high. This is an example of what it looks like in terms of the forest. So automatically with LiDAR technology you get information on the vertical structure, which on a photo we don't have that ability. From an inventory point of view, very simply, the first return we get back from the sensor, it gives us the top of things. So the tops of trees from an inventory. The last return or the first return in an opening, we get a very detailed picture of a digital elevation model, a detail that we've never had before. From an inventory point of view, we're thrilled because all of a sudden now I can take the digital surface model, subtract the ground, the digital elevation model, or the digital terrain model, and I end up with the canopy height model. So now no matter where I look, I can measure the height going across the landscape. And height's one thing. LiDAR is used all over the place, different parts of the world for many different things that we've demonstrated here in Ontario, a whole suite of things it can be used for. But because Al only gave me 20 minutes, which is now becoming 5 minutes, I can't talk about any of that stuff. What I want to talk about really is just focusing on the inventory attributes because that's where most of the research that we're conducting is focused on. And I highlighted biomass, but we're able to produce this whole suite of attributes from that LiDAR data. Some people are expecting equations from me, but I'm just going to go with sort of some results from some preliminary work. So what I'm presenting here is sort of different forest types across the top, models that have been built from very low density LiDAR, which is about half a hit per square meter, and give you an estimate, maybe for the first time in Ontario, some average error estimates. So right now, things like the tolerant hardwood forest types, anywhere on the land base, I can predict basal area plus or minus 2.4 square meters, or with an error average error of about 9.7%. Same with volume and density. Density is the worst variable with LiDAR to predict, but if you look at sort of the average stand diameter, again, very low percent errors. Height's a no-brainer with LiDAR because that's what LiDAR measures, but the one for us, too many remotes here. The one we're talking about today is sort of biomass estimates. So with LiDAR technology for these different forest types, you can see sort of the range of errors. The ones in percent are in brackets, 12. The red white pines, a little bit higher. Mixed woods, so plus or minus 10, 15, 20% for our volume estimates in a biomass context. This is total above ground biomass. We can also do sort of the stem and branch biomass breakdown as well, because if you remember, that's what LiDAR is hitting, the tops of those trees. What we basically want to do is apply that to the land base. So here in this sort of cartoon, we basically grid up our land base and we take this vertical structure, this point cloud information of the LiDAR data, and through modeling and statistical techniques, every grid cell gets an answer. So in this case, it's an average height model. So what we end up with across the land base is for every 400 square meters, I can give you the average height. Or I could give you the average volume. This is gross total volume, but because we're talking about biomass today, I could basically map out the biomass. And what you'll see is if you zoom in into a single stand, there's a range of biomass. The LiDAR is able to give you that answer at that type of scale. Remember, we're not sort of interpreting it, we're actually measuring and predicting the biomass because we have this detailed vertical information. This gives you an idea. I mean, here's height. So you can also see we're hitting regeneration where the ground is identified, but you get that vertical structure. So the people that are interested in habitat, you can immediately see the benefits of having a LiDAR data set to work with habitat modeling because we always try to use other surrogates like species and age to sort of come up with vertical structure. Vertical structure aside, what we basically want from a wood flow or from a biomass perspective is horizontal structure in terms of diameter class or size class. With the LiDAR data, we're actually able to extract either diameter class distributions or size class distributions. And very quickly, this is one of the tougher situations, which is sort of the uneven aged distribution in our tolerant hardwood stands here in Ontario. We've been able to recover that shape very well from the LiDAR data and equally also estimate size class distributions. So you know, in our current forest inventories where we have tolerant hardwood stands, we know they're uneven aged, but the inventory still gives it an age. But we say that's really not the piece of information we need. We need to know what that structure is in the stand to determine whether or not it's going into single tree selection or shelterwood. We could light up an inventory with this structure piece and allow the resource managers to make that decision from the office. And again, somebody's going to throw something at me. I'm not trying to get people out of the field. I want people to go into the field to measure this stuff. This is just sort of a strategic planning level, but that links directly to operational. We still need to have people going to the ground to do these more detailed measurements of things like quality for hardwoods. Last piece, I want to talk about the imagery side. You notice in the LiDAR side, I didn't talk anything about species. LiDAR does not give us species currently. Right now, we believe it has a chance of doing hardwood versus conifer, but we're relying on imagery to do the species piece. And the work we're using is work by Drs. Don Leckie and Francois Goujon from the CFS out in Victoria, where they were using satellite imagery and computer technology to scan the images to come up with an inventory. So very quickly walking through, we end up with, this is a digital imagery. This is a Leica ADS-40. This is the imagery that the Ontario government is purchasing for the area of the undertaking where we do forest management. It's 16-bit imagery, 4-band. I have infrared, red, green, blue. Here's an example of just true color, the red, green, blue. I can stretch that, and all of a sudden you can see how the species seem to jump apart. We can use that information with computer technology. First thing in the process is we have to get rid of all the noise. So we basically use either a spectral signature of shrubs and roads, or we use LiDAR data to mask out that lower noise. From there, we basically run a couple different techniques. This one is called valley following. The software goes around and looks at each crown, and it basically draws a circle around the crown using the dark pixels around each tree. From there, we end up with a crown bitmap. So we convert that vector to a bitmap, and all of a sudden we sort of identified all the crowns in the forest. Where I'm driving at is away from a stand polygon, but to a tree polygon. But I don't want to stand up here and lie and say that we're identifying every single tree. Some species were very good at doing individual crowns, but in a lot of cases, especially hardwoods, if you think how they are shaped in terms of a large bowl and then multiple branches, we tend to either over-segment hardwood crowns or lump them with its neighbors. So we're talking trees and tree clusters at this point in time. But that's the first step. What we need to do is go out and teach the computer what those species look like. So either having, in a 3D stereo environment, we have interpreters identifying species of red pine and white pine and jack pine and maple, or we have people on the ground going out there and actually on paper or on a tablet with GPS technology identifying this is a maple, this is a jack pine, this is a beech, and we teach the computer the species. Some of the species separate very well. In the boreal forest, we're quite lucky. As you can see, the ones I've circled, they separate spectrally reasonably well. Unfortunately, in the Great Lakes St. Lawrence forest, the separation between hard maple and beech and yellow birch is not very good, and so we're struggling with other ways to do that on the side. We end up with taking that blank bitmap and now identifying each crown with a species. From there, if I zoom in a bit, you'll see this is sort of what you're looking at. So you can see some different shaped crowns. Ultimately, the software has also an option to push a button and actually will give you an unsupervised classification where it will drive right up to stand polygons. But you also have the option of querying the data and deriving your own polygons to meet your inventory objectives. Another output of the model is basically to give you the species composition based on that analysis that was done, also the height, and also will give you a density count because for every single polygon, it's counting it as one. But again, remember, there's still issues with single trees versus clusters of trees. So I'm very happy at the stand level with the percent estimates we're getting, but the density estimates are off. How well are we doing from the species perspective? Overall, right now, we're getting numbers about 70%, but I put a big caution beside that because we're sort of reporting on our training data. We're now out there doing independent validations so that we can come back and tell you, plus or minus, this is where we are with our species classification. Surprisingly, some species work very well and others don't. In wrapping up, basically, the imagery classification part of our efforts are moving along quite well. It's basically another tool for the interpreters, not out to replace people. It's basically to provide a first pass and help interpreters make their calls. But it is very objective versus subjective. The computer does the same thing every time. If you want to do a better job, you retrain, the computer can do it fast, quick, and across the board the same. Where interpreters, when you have the human person, with different people working on the same management plan, you can get sort of certain pieces their bias versus another one. So the computer offers that ability. We are driving towards individual tree inventories, but as I mentioned, right now we're focusing on trying to refine that work because of the clustering that happens in hardwoods. In the LiDAR side, we are basically operational now. There's probably, I would call them misconceptions about the cost of LiDAR. I think people should look more at the value side of it than the cost, which again I would debate on whether it is expensive. We've also proven that more is not always better in the case of LiDAR. We don't need high density LiDAR to give you the results I showed in terms of stand level attributes. We are taking this information and we're rolling out a 650,000 hectare inventory on a Northeast planning unit, and next year our plans are to do both LiDAR and ITC on 1 million plus hectares to demonstrate to people the value and the fact that it can be done. And again, the LiDAR stuff is just the beginning in terms of the inventory. There's all kinds of other pieces of natural resource supporting information that LiDAR can provide, and we're just continually amazed and excited about how they are playing out as we move forward with this project. Thank you.